My name is Jim Graham. I'm the 2D graphics architect for Java and JavaFX. And today I'm going to tell you about some new APIs we introduced in JavaFX 2.2, which went into Java 7. Numbers get confusing. We'll sync up in 8. And it's for accessing the ability to access pixels in images and a few other objects in JavaFX scenes. So, sorry, set focus. Okay, so why do we create pixel access? It seems like we moved from, in the Java world, we've moved from dealing with individual primitives and pixels to dealing with a scene graph and letting us do a lot of the work behind the scenes for you. But that doesn't always meet everyone's needs for a variety of reasons. Sometimes you just need to do something that we haven't provided in terms of rendering or effects, and you know how to do the work, but you have no access to the pixels, no ability to give us some pixels or get pixels from us to modify. So this will meet that need. You might want to create your own image loader or image writers. But prior to this, all we offered was the ability to point us at a URL or a file to load an image from. You may have some legacy code which involves custom operations on buffered images or some work in SWT involving images, and you need to get those images into a JavaFX application. So this will provide a pathway from which you can through which you can import such images. And finally, we've had hidden unsupported APIs for doing snapshots of nodes and scene graph trees. But along with this support, we created a public API for creating snapshots of trees and parts of trees. So let's take a quick look at the API, and then I'll get into some demos and examples. Basically, the way you get access to the pixels is you get an object called a pixel reader or a pixel writer. And there are several places you can get those. On the basic image, which you can load from a file, you can get a pixel reader, which means you can have read access to the images you load. We don't have write access to the images you load. Instead, we created a special class called writable image that you create with a width and a height. And you can still get a pixel reader for reading from it because it's a subclass of image, but you can also get a pixel writer and write to it. So that sort of is the destination of any image operations that you might want to have. Finally, we introduced at the same time an API elsewhere in JavaFX called the Canvas API, which has a graphics context which lets you render into it, and that also lets you get a pixel writer so you can supply pixels in kind of a put image operation. I'm not going to go over Canvas today, but that'll be a talk tomorrow, but that's another place where you can get one of these pixel writers. So Pixel Reader is a pretty simple API. It has, there's a few more methods here because you'll see that ellipsis there because I combined a couple of methods, but basically you can get an individual pixel either as an integer for quick access convenience or as a color if you need an object to work with the color. There are several methods for getting pixels in bulk. Actually, there's 3 methods for getting pixels in bulk for larger operations, and if you want to work with the pixels in a particular format other than this integer RGB version or other as a color. And finally, you can get a pixel format which describes the underlying pixel format that we use internally in case you want to optimize your bulk transfers to be in the same format. A pixel writer is almost perfectly analogous to that. All the gets are just sets, and they take the corresponding argument. There are several set pixels methods as well, and also a get pixel format, which hopefully will agree with the pixel reader if you're talking to a writable image. And it basically lets you know which format is optimal for transferring bulk pixels. The pixel format is not extensible and not doesn't include every format under the sun. We focused on formats we thought would be most useful for casual to intermediate use of reading and modifying images. So there's 4 formats that are full color. A byte format if you prefer to work with byte arrays, individual components in a byte, and an int format in case you would rather work with pixels being one single integer value. Then for reading, we also provide ways for you to give us data, opaque data in 3-byte format, or even indexed data if you have some of that you need to provide to us. The pixel format includes an is pre-multiplied method, which you could infer from the type. The types that end in _PRE are the pre-multiplied formats, but if you have a pixel format, you just want to know if it's pre-multiplied, you can ask that. Is writable is true for the full color versions, meaning that we can use those as a destination to stick pixels, but any of them can be used as a source to supply us with pixels. And finally, it has a getArgB method, which can look into a buffer, figure out all the appropriate math to find the pixel in the buffer, and return that in ARGB format. That's not meant to actually do work. That's just meant to be the canonical reference implementation of the way this pixel format works. But typically, you would look at the type of the pixel format and write your own code to do that kind of access. You wouldn't be using that method as your primary means to perform the access. But it's there in case you have an unknown pixel format and you need to get the pixel data out of it. The writable pixel format extends pixel format and inherits almost everything, but also provides the canonical reference set ARGB method, which again is not meant to be used for work. It's just there to provide a reference implementation of the way the math is supposed to work. We provide static factories to get these as opposed to instantiating them yourself. This is so that we can grow in the future and basically have also some of these can return a singleton instance. Some of them need to create a custom instance on the fly. So the factory will either be a get such and such instance factory if it's a singleton, or a create such and such instance if it needs to provide a custom one for each one. The only ones that need to provide custom ones are the byte indexed instances, where you give us the color map and then we return the pixel format that uses that particular color map. All the other ones are pretty much singletons. We can return the pixel format that specifies that particular byte format. And they pretty much map the enum that I showed earlier. And the 4 that are full color return writable pixel formats. The others that are not full color return only a readable pixel format. So the various get pixels methods that are available on a pixel reader, they all take an XY width height rectangle region that specifies the rectangle of the image you're getting, or in the case of a pixel writer that you're setting. There's the third one is the format for dealing with a Java new IO NIO buffer, and all of the pixel readers are tagged. They're generified so that they have the appropriate NIO buffer defining their underlying pixel data format. So it'll either be a pixel format of a byte buffer or a pixel format of an int buffer. And it can read from that corresponding buffer, or it can read from the corresponding Java primitive array type that corresponds to that buffer. So you can only use a pixel format of a byte buffer for the method that will get pixels into a Java primitive byte array, and you can only use a pixel format of int buffer for the method that gets the pixels into a Java primitive int array. And then, of course, the type has to agree for the third format that uses the generified T specifier. It's somewhat strongly typed in that we associate the byte buffer method with a Java primitive byte array, but again, Java uses type erasure, so you could construe to compile a program that calls the method with the wrong data types, and you then get a class cast exception at runtime. So it's strongly typed insofar as writing your code if you use generics. You notice that the Java primitive array formats allow you to specify an offset into the array where you want the data to start, and the scan stride, which is expressed in terms of the number of primitive array elements to skip between scan lines. The version that takes a NIO buffer does not provide an offset because we assume that you're going to position the NIO buffer at the location you want us to start putting data into there. The other interesting thing to note is that this is a pixel reader, but the getPixels methods use a writable pixel format, and the reason is because we are writing to your buffer, so it has to be a format that is writable. Even though you're getting, we're doing the writing, so we need you to supply a writable format. The pixel writer, on the other hand, you notice it takes non-writable formats because we're reading the pixels from you. They can be in any format because internally we store them in full color. It's basically analogous to the getPixels methods. You specify an XY width height rectangle that you want to write the pixels into. There are versions that are typed by an IO buffer but take a Java primitive array. There's the fully generified version that takes the matching NIO buffer to the pixel format type. And finally, there's a way to hand us a pixel reader you got from someplace else and a source location to use in reference to that pixel reader, and we will extract pixels from a pixel reader directly into our image. Again, it's somewhat strongly typed within the constraints of Java generics. The NIO buffer version assumes that you've positioned the buffer prior to handing it to us, so it does not take an offset, and it provides easy transfer of pixels from any pixel reader. The pixel writer talks to pixel readers, but we didn't really provide the other half of that method because this was an easier way to implement it. So the exact formula for how we will access your buffer for any pixel in the region that you specified, the XY width height region, the corresponding Y is multiplied by the scan you give us. Then we take the corresponding X, we multiply it by the pixel elements that are inherent in the format. And for some formats, if there's multiple pixel elements, we then assume that the components are in adjacent elements of the array starting at that location. You'll notice that the Y is multiplied by scan, but not also by pixel elements, because we assume that you've already multiplied your scan stride by the number of pixel elements that are necessary. This allows you to have a scan stride that is not a multiple of the pixel elements in case you want to, for instance, have 3-byte data in lines that each individual line is word aligned. In order to do that, you need to have your scan stride not be a multiple of your pixel elements. So this formula does not imply that the scan stride has to be such a multiple. You will get an array index out of bounds exception if you don't provide enough array space for what you've specified with your parameters. It's undefined how much of the data we will access before you get that out of bounds exception. Sometimes we do a bounds check ahead of time, and you think there was data we could have accessed that we didn't, but we don't define that we access all possible data before we throw the exception. We throw it whenever we discover it. So unless your entire rectangle is in bounds, essentially the operation is not defined how much data will be transferred. The number of pixel elements should be relatively inherent if you know how to deal with the pixel format. If you don't know how to deal with the pixel format, you probably shouldn't be using these APIs, but there's one element for any of the int formats, And for the byte indexed format, that's also a 1 pixel element. Byte BGR is 3 pixel elements per pixel, and the byte BGRA full color byte version, oh shoot, that should say 4. It said 4 in an earlier version, but I did some editing. So I'll have to edit these slides after the fact, but obviously 4 bytes for byte BGRA types. The set pixel is pretty much, this is the get and set pixel of the NIO buffer. And the only difference here is that we do absolute gets and puts relative to your position. So when you get back from this method, your buffer position is not modified, but we took it into account when we did the data accesses. But it's essentially otherwise analogous to the Java primitive arrays with your buffer position providing the offset into it. And again, the position and limit you have in the buffer, so if you specify a limit that doesn't allow us to read enough data, you will get the appropriate exception you would get from an IO buffer. Just a quick reference for how to unpack the data that I was showing earlier, the set RGB, the set ARGB and get ARGB methods use an integer pixel in this format, which is 32 bits, 4 bytes, packed from most significant byte to least significant byte as if you were expressing a hex constant. The first 2 digits would be the alpha, the next 2 digits would be the red, the next 2 digits would be the green, and the last 2 digits would be the blue, placing the blue in the least significant byte and the alpha in the most significant byte. And this is just reference code for how you would do the shifts and ands and ors to unpack and pack the data. Note that the one that packs it up is going to assume that all the components are within the range 0 to 255. If they're not, then one component will end up throwing some extra bits into another component and you'll get a random result. We assume you've done the appropriate data clamping yourself for that particular piece of pseudocode. Finally, this writable image pixel reader, pixel writer API is paired with the Snapshot API that essentially uses writable images, you can see here, as the way to convey the snapshot to you. So there are 2 variants on scene and 2 variants on node. Each one of those will have an immediate version that returns you the image immediately when the method returns, and also a callback version, which will be done asynchronously. The only other difference between the scene and the node methods is that the node doesn't have a lot of context we get from the scene, so you supply that context in a parameter called a snapshot parameters object, and it basically contains the data that would have been in the scene that allows us, like the transform that came from all of your parents from the scene down to that node, the fill that you have gotten from the scene, the viewport, the camera you would have gotten from the scene, the depth buffer Boolean, which tells us whether there's a depth buffer needed, and a viewport, which would have been essentially the data we got from the stage when some of this comes from stage, I guess. The viewport would be simply the size of the stage that the scene would have been in. But the version that uses scene, we infer all of that from the scene itself. Again, both of the scene and node contain a version that uses a callback, and the callback will basically your callback doesn't need to return any data. It's a void callback. We provide a snapshot result argument, which contains the image that we rendered into, and also the source, the node or the scene that you called it on, and the snapshot parameters that you gave us if it was the node version, or null if it was the scene version. And the source and snapshot parameters are just there for if you ran several of these and you need to try to figure out which result is being returned, you can use the source and the snapshot parameters to try to figure that out. although typically you're only going to have one outstanding at any given time. So why would you use the callback version, given that you have to construct a callback and it's a little bit more of a pain? And the answer is two reasons. One is when you do it in immediate mode, we aren't in the right thread or at the right stage of processing to immediately render anything. So we have to basically do a handoff to the other thread. We have to first synchronize a whole bunch of state, do a handoff to the other thread, have it render for us, return that data to us, and we block while that's happening. That's a big disruption in the flow of control of a JavaFX application to start with. And then the second reason is that some of that synchronizing operation we had to do in order to transfer the control may have been duplicated effort that would have happened at the end of your pulse. So a pulse will allow you to respond to events, modify the scene graph. At some point we need to transfer over to rendering. There's a process of synchronizing the data over to the render thread, and then the render thread can do its work. If you use the non-callback version, we have to sync right then, and then again we'll have to sync at the end of the pulse. So you duplicate that work, in addition to the fact that you're forcing a thread switch and a block. So there's two reasons why callback would be better. However, it may not matter to most of your usages of it, and so the immediate mode may be more convenient and may not impact your performance enough to worry about. Especially if you're like writing documentation, you just need screenshots of your application, performance isn't an issue there. If you're doing a thumbnail of one state of your application once, it may not be an issue. If you're doing frequent snapshots for any reason, then you might want to start using callbacks. If you notice that it's impacting your application, then the callback version may be a way to have less impact. So I'm going to get into some examples here. The first example is going to be custom filters, and I have actually a couple of different versions of that. This one I sort of wrote to be example code, and it's just it loads two images and performs an edge detect filter on them. So if I click on it, that's the edge detected version of the image. I did an individual edge detect on the red, green, and blue planes separately. I could have done a luminosity and then done a single edge detect on the luminosity, but that's just the way I wrote the example to be simpler. So two images and their edge detected versions. The code is fairly simple. Loads two images, calls a filter method on them. The filter method returns actually a writable image, but you can just treat it like an image. Throw them in an image view and they can appear on the screen. I install a mouse handler, so when I click, I just go to the next image in the array to cycle through them. A couple of helper functions. One just accumulates the red, green, and blue samples from a pixel reader. I was going to say, why am I passing in a rectangle? I'm not. I'm passing in an X and a Y, and I'm telling it the width and height of the image so it can do its own bounds checking here, because I don't want to access outside the bounds of the image. I want to treat those pixels as if they're transparent or black. An array to accumulate in, and a multiplier that we can apply different scale factors on different pixels. This combine function is just a way to take the horizontal edge and the vertical edge results and combine them into a single result. So the basic operation will construct a writable image of the same dimensions as the source image, get a pixel reader from the source image and a pixel writer of the destination image, create some accumulation vectors. For each pixel in the region, it zeroes out the accumulation vectors and then uses this simple convolution kernel to perform an edge detect. You can see that it accumulates the current column. It does not accumulate the current column at all. It accumulates the current column to the right and to the left with opposing opposite sign weighting factors. That means that if there's a change from the pixel row to your left to the pixel row to your right, this will accentuate the change. If they're the same data, the results will end up being 0. So that's basically the way an edge detection filter works. And you do it once vertically and once horizontally, where, again, you just turn the kernel on its side. And then you take those two results that are accumulated into either accumulate horizontal or accumulate vertical, and I just combine the results, construct a pixel, and write it to the pixel writer of the destination and return it. And you can see doing the simplified writing each pixel individually and fetching each pixel as it's needed, which does 12 pixel fetches per output pixel and 1 pixel set per output pixel, and it took a couple tenths of a second. So if that's just something you have to do at startup to one image, that's not an issue. You might want to use the bulk transfer methods if you're doing this in any kind of batch setting or a lot of images. The other examples I wanted to show you, there is, Jasper is actually going to talk about in one of his talks. Somebody had written a whole bunch of image filters for buffered image, and in a few weeks they converted it over to using the pixel reader, pixel writers methods. So this is essentially just an example of a few of the filters that they provide being run on. This is a JavaFX application, and he just wrote an example that showed off a few of them. So this is just driving that package that is available on the net. I believe they had like 50 different kinds of filters you could use. And then he took one of them that provided various kinds of lens blurs and duplicated something you find in Photoshop, which is a tilt and shift blur kind of effect. And you can change the parameters on the fly, move this around to change what's being blurred and by how much. And you can change the bloom threshold, which, as far as I can tell, just sets the grass on fire. But apparently people who know Photoshop know what to do with that to do exciting images. The next demo is creating synthetic imagery, and I have a couple of examples of that. The first is, before I go to Zoom, I'm going to go to the custom patterns. So you can use a writable image in an image view. I've already shown that. You can also use it as part of an image pattern. So if you wanted to create a background on the fly, you could construct your own pixels, put it in an image pattern, and boom, it becomes the background of your application. And an example of why you might do that is that you don't know what color you want the background to be until you get running and you load their image and you want it to match their image, or you ask them their favorite color, who knows what. You can't have a canned image for every possible runtime consideration for some uses, so this allows you to construct an image at runtime that you use as a background. This one's a fairly simple one. I just create this kind of corrugated metal pattern, and then I cycle through the colors. I'm not seeing a color shift from here, but I'm seeing it on my screen. Is it shifting colors over there? Okay. At this angle, I don't see it. But basically, I have this base file which sets up a rectangle and asks the subclass to make a pattern, and then it creates a simple property and animates it, and that changes the hue over time. And it just puts up the window for you. The metal pattern is designed around a simple 6x6 image using that pattern to create the sort of corrugated metal look. And then of course, it's a 6x6 image, but it creates an image pattern that is scaled up to 30 by 30 pixels just so you can see it on the projector. And another example of how you might do this is if the background should contain information you don't know until runtime, like this one, I basically render the date using Snapshot and then animate, once a second I re-render it. It could be the status of the nuclear reactor, whether it's gone critical, and it could change red to green depending on how the coolant level is, and it could say critical when it's critical, or it could say nominal when it's not. That's an example where a limited set of pre-canned images might have worked, but if the status was something that, perhaps you want to show the percentage, that would require 100 images, or you can just do a custom image. And this particular example uses Snapshot on a node to, a text node to render the current date. And then there's one that basically shows using it with a scene. So it's basically just the choice between using the method on scene versus the method on node, but both of them do essentially the same thing. An animated date, changing the color. I sure hope the color is visible over there. Yeah. Okay. So those are the examples of custom, Zoomy. I didn't do Zoomy. I have to do Zoomy. So Zoomy was a piece of eye candy I wrote several years ago for a swing talk. And it's a relatively simple concept. Let me just show you what it looks like first. I will use this version. It basically throws some color into a scene and then runs an effect filter on it, which can sort of stir the color around. And the filter's a incredibly simple filter. All it's doing is, for every pixel, it's choosing not necessarily a random, but it's choosing an algorithmic location to grab the color information from the previous frame. So if the color information is, for instance, closer to the center, then it will appear to be zooming out as you apply it on successive frames. Some of these choose sort of this one's just a random distance. This one is choosing interfering sine waves that cause that swirling pattern. But basically, to apply that filter, you need to essentially perform a linear interpolation on 4 pixels given the location you're supposed to be sampling from. So I wrote successive versions of that. There's a base, Zoomy base. Hello? Why can't I double click this? There we go. This just basically sets up the windows, sets up the definition of the maps that it applies, creates the frames per second label, and makes sure that that's all going to show the correct frames per second. In every frame, it adds some color, it applies the map, and it swaps the buffers so that the source for one frame becomes the destination for the next, and vice versa. But then I have several implementations of how to do the actual work using image ops. So the simplest one, to displace a pixel, you can get the colors for the surrounding pixels that you need to interpolate, and then use the color methods to interpolate. This is very simple to write because the color object provides you the interpolation, and you're just grabbing the pixels you need without having to do any indexing yourself. And then you set the color when you're done. And if you do it that incredibly simple way, you get 3 to 3.5-ish frames per second. And the interesting thing is that that's a 500,000 pixel sized window. You're creating 7 colors for each pixel to perform the operation, not including the interpolation method. So of course it's going to run really slowly. The next sophisticated version you could do would be, instead of creating all those color objects, you simply get the integer pixel. So it involves 7 million fewer, actually 3.5 million fewer objects per frame being created, but still 3.5 million function calls to actually get the pixels. And then I just use a helper method in another file to perform a linear interpolation on 4 integers. And this version bumps us from 3 to 3.5 frames per second to 6 to 6.5 frames per second. So not quite double the speed to get rid of dealing with all those objects. Then if you want to amortize your access to the image by reading the data ahead of time so that you don't have to be doing a method call per pixel that you sample. I wrote this version, which it overrides a method called load data that the main file calls, so we can perform a get pixels on the entire image into our array, and then we can just do array accesses to get the data for the pixels. And notice I have to calculate my own index, so it means I have to understand the pixel format enough to be able to know how to calculate that index. It's fairly simple in this case. I just used the integer, one of the integer formats, which was easy to access. And when I'm done, I still call set RGB per pixel to stick the data into the destination. Doing that, we were at 6 to 6.5 frames per second. We're now at 17-ish frames per second. So that's not quite, that's 2.5 to 3 times faster to avoid 4 method calls per pixel. But you notice I still stick it back a pixel at a time. So what if I created 2 arrays, a source array and a dest array. I load my data by grabbing the entire image into the source buffer at the beginning of the operation. I store the data into a destination array, which I then write back to the destination at the end. This eliminates the 500,000 method calls to set the data back. And we were at 17-ish frames per second. This version takes us up to over 30. So roughly double for not having to do that method call per pixel to store the data back. Now you notice I'm still reading it every frame, even though I've calculated the previous frame. I already have that data in one of my buffers. So I can skip the read operation by using a swap of my buffers. So this is roughly the same. It doesn't override the load data. It just simply overrides swap buffers to switch my internal integer arrays. But to do this now, it had been filling one of the images with the color. I spray some color into the scene every frame just so that it has something to stir around. I have to now do that to my own array, so I overrode the fill method to inject the color into my own array. But other than that, it's roughly the same. I'm just saving myself having to load the pixel from the source image every time. So we were at 36 to 37 frames per second. This takes us up to almost 40. So that wasn't as dramatic as getting rid of the set pixel call per pixel. Finally, how much time am I wasting by doing all of these linear interpolation work in my method? So I wrote a version that did a really crappy, I just copy the pixel. So I figure out what pixel you wanted, I copy it, and it's going to look ugly, but this gets rid of a huge number of my own calculations per pixel. How much impact will that have compared to the overhead of all the image I/O operations? And in this case, I was at almost 40 frames per second, and now I'm in the high 70s, so it's not quite double. So basically, getting rid of my own calculations doubled the performance. It shows you the ratio between how much time is being spent with my own filtering operations versus the pixel access operations. And I forget what the difference with the optimal, the optimal one is, when I did that first one, I'm still calling this displaced pixel from the main class, calls displaced pixel on each pixel, which means it's still doing all those method calls. What if I just overrode the whole apply map operation and just inlined it all so the hotspot could go to town and optimize this? I was at almost 80 frames per second, I think. And this gets me to, the numbers are quite different than I'm hooked to the projector, but yeah, it bumped me up a bit before. If I'm just running this in without connected to the projector, I went from about 80 to about 105 frames per second. So obviously my chip is having to do dual work here or something. Anyway, so that gives you an example of the relative performance that you can see from all the various methods that we created for accessing pixels. Some of them are more convenient, they'll cost more. That may not matter for your operation. If you need maximum performance, you're going to want to do bulk pixel operations, and that's fairly obvious application tuning. But there's an example that demonstrates the need. And then, one last demo. I wanted to show demo of Snapshot for thumbnails. And there's really just one demo for that called thumbnails. And so what I did here was I created a hypothetical business browsing application that basically just creates all these random little nodes that have some combination of these marketing buzzwords in them and links them with little lines so you feel like you're actually analyzing your business, but really it's just a random display. And I create 16 of those hypothetical random project analysis things. And then I create a row of thumbnails so that you can click and switch to different views. And then within the view, I have a mouse handler that lets you zoom into various nodes. So when you run it, you end up with, ooh, look, I'm analyzing my business here, and then there's all these different other analyses down here. So if I click on that one, I go to that. If I click on this node, now I'll do it once, as you see. So it animated there, and then look, if you watch down here, I actually update the thumbnail when it gets to the destination. So zoom, 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 new thumbnail. Zoom, 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 new thumbnail. Zoom, 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 new thumbnail. So it just basically running the thumbnail with a variety of transforms, and you can, oops, and I have no scroll bar down there. Yep, screen's not tall enough to show the scroll bar, so I can't scroll to the other projects because there's a scroll bar that's off the bottom of my screen. So all this ends up basically in, the interesting part was this Zoom project basically just changed the transform on the root of node. If you click on a different project, it just shoves a new node into the view pane. And every time I do one of those timelines to change the scale on the transform, I set an unfinished that when it's done, it calls make thumb again. And make thumb basically sets up some snapshot parameters to perform a scale to the thumbnail size. It sets a viewport to match the image, and then just calls node.snapshot into the image, and boom, it updates on the screen. I didn't have to tell anything that it was a new image. I just called snapshot, the image got updated, the image view showed the new view. So that is that example. And to wrap up, how does this compare to buffered image? Well, a buffered image we implemented with a number of partners like Kodak and I think at the time Macromedia was talking with us, and Adobe, and they had grand plans to use this for everything that one might possibly use for Photoshop Professional to do and satellite imagery and medical imagery. So we basically wrote an open-ended set of formats that you could customize as much as you wanted to deal with any kind of image data that you would ever need under the sun. And it ended up with an API that confused a lot of developers. How do what is a raster? Why do I have to dig down into it? And what the heck is a sample model, and why do I need it? Here we went with a limited set of formats that would be familiar to the vast majority of developers. And we focused on that for the first release. We may provide something more sophisticated later, but remember, we still have all of Java with buffered image that can deal with those markets that need incredibly detailed custom images with 100 different kinds of planes of data. And using the pixel access, you can import data from a buffered image quite easily. And so therefore, we essentially leverage now all of the advanced imagery that was created for Java now in JavaFX through an import mechanism. But to keep the API on the JavaFX side simple, we're focused on just the core formats developers tended to use. Buffer and image was created before NIO created its buffers, so it had its own kind of rough equivalent to an NIO buffer that it used for data storage. Here we just went with NIO buffers and raw Java arrays for pixel transfer to keep it simpler. Buffer and image also, you could dig down and get the actual array that we were using to hold the data. And this caused two problems. One was that we would then never be able to basically store that data in a native memory. We had to store it in a Java accessible array because you could grab the Java accessible array. Also, you could go and start modifying pixels and we wouldn't know when you were done to update anything. And basically, if you ever grabbed the array, we would permanently mark the image as not hardware acceleratable ever again. So here we've gone with more of a batch transfer operation that allows us to maintain hardware acceleration despite the fact that you're modifying the data. So summary, provided a way to get pixels from your images, created a new writable format that allows you to give data to the images, and also to a canvas, which we'll talk about canvas in another talk tomorrow. Provides a bunch of methods from the convenient, give me a pixel at a time, even in a color object so I can play with it, down to bulk transfer into an array, and then I will figure out how to pull the pixels apart myself. Common pixel formats that most developers are used to dealing with. It won't replace effects. It's not intended to be a way to get hardware accelerated image manipulation. This is for, I can write the Java code, and you can't do this with an effect, so now I have a way of doing it. And we have internally some optional packages which provide buffered image and SWT import and export, and this mechanism is now how they do their work. So, and it's basic, it was like 10 lines of code to import a buffered image or export a buffered image from JavaFX using these facilities. So it provided access to legacy code that is fairly rich with image processing. So I'll open up to questions now. Your hand went up first, but this is still up. I don't know.
The question I had was, I saw on the OT forums a while ago, there was a guy bringing in VLC player.
I'm sorry, the echo's in here. It's hard to.
He was doing the VLC player, and he was bringing it into an image, and the end result was that it was going slowly until he changed the pixel format. And I was wondering if there was any kind of advice you would give to which pixel format people should choose.
Well, earlier on I showed that the pixel reader and the pixel writer will have a get pixel format method on them that tells you the pixel format that we're expecting. So if you stick to that pixel format, which means you'll have to do a switch on the enum. Typically right now, almost all of our images are byte BGRA pre-multiplied internally. But also, I think there was work that did not make it into 2.2 that optimized all of our pixel transfers. In 2.2, we shipped with basically calling get pixel, set pixel on the reader and writer for every pixel in a bulk transfer operation, which is going to be slow. And shortly after 2.2 shipped, there was code that went in that basically did direct conversions of all the formats from and to. So it might get better in the next release. It probably will get better in the next release, but the intention is that you're supposed to use the get pixel format.
Certainly when you changed it to the other method, it would be much faster. Perfect.
Yeah.
It's just the wrong method.
Yep. And then back there.
I've got two questions. Well, first of all, I support ICC profiles. And secondly, when you have large images, is there any concept of tiling so that you don't have the whole image very many times?
So the question is whether we're going to support ICC profiles and tiled images for images that are too large to really deal with in a single chunk. And the answer is no. It goes back to that we wanted to keep it simple for the first release. So there's nothing here that deals with it yet. we know this will need to grow. We're not sure how we're going to do that yet. We wanted to, our goals were basically to not get in the way of hardware acceleration and to be accessible in terms of not confusing developers. Beyond that, moving forward is work that has yet to be defined, so you could start up a discussion on any of the mailing lists to how you would like to see that added. And also, this also comes back into the buffered image import-export. We have all of that with the existing Java stuff, so it was enough outside the core needs that we don't mind creating a temporary dependency on the regular Java stuff, use that and import it into here, because the applications that tend to need to do that are not going to be impacted by having both the JavaFX stack and the AWT stack at the same time. So there's two answers. One is we didn't want to focus on that yet, but that doesn't mean we're not going to, and you can do that using legacy code and import it. And then down here.
Yes, linked to those two questions. The first one, in Swing, we discovered after a while we had to convert buffered image to compatible buffered image to get hardware acceleration. So this is in the case that the color space needs to be changed. Is there any such implicit conversion, or do we need to manually look at the pixel format, try to find out what's better and change it?
So the question was that when they were using buffered image with Swing, they discovered that some of the formats would not end up hardware accelerated, and they had to play with the color format they were using and the color space they were using. And how does this differ? And the answer is that we specifically designed this to not get in the way of hardware acceleration. So that's why we do the bulk transfer methods. When you give us the data, we will make sure it's in a format that we can hardware accelerate. It should have worked for buffered image. We should probably talk after, because unless you got the buffer of pixels from a buffered image, all buffered images should have been mirrored in VRAM and hardware accelerated. But if you ever got that buffer, we'd stop doing that, and then we might have needed to do a conversion every frame.
Most of the time when we load an image through image IO, we would have needed to convert it to a compatible.
Wow, so what came back from image IO? There was also bugs in image IO where it would leave an image in that state of, I've grabbed the data array, now it's not acceleratable.
If we load through image IO then convert to FX, we should have a proper format by default.
Exactly, the FX image should always be acceleratable, currently, yeah.
Second one was linked to the other question that so for medical satellite, we still need to go through Java advanced imaging or what's available in Java 2D, and maybe later on you will have tile image and other things like filter, kernel operation and such. But currently we still need to rely on legacy code and then convert to FX to display.
Okay, so I'm just going to summarize that as another vote for more advanced imaging in JavaFX. Okay, and then did you have a follow-on?
One last question, which is, it looks to me like you're focusing essentially on ARGB as the display format in the file. So in your example where you loaded a JPEG, if I had provided an index for a CMYK or ICCK JPEG, would the software, how would the software handle it? Would it just try to treat it as an RGB, or would it run some kind of exception?
How would my software have handled it?
How would JavaFX?
JavaFX, whatever format it's using internally, like if our JPEG loader decided to load it into one of those other formats, the question, let me repeat, is what if you had a source image that was indexed or not one of the demo seemed to be focused on ARGB formats. What if you had loaded an image that was not in one of those formats? How would the software have dealt with it? And the answer is twofold. One, the result of loading the image is not necessarily how JavaFX internally represents it. Sometimes we do have representations that are not ARGB internally. And if you do get pixels on an image that is in another format, we can convert on the fly. And if you do set pixels, and suddenly we have to deal with alpha, we will internally upgrade or change it into a format that can take the data you gave it. So if we loaded a GIF, for instance, and we were representing it internally in index format, I'm not sure that we do that. But if we were, and you handed us an arbitrary color, we would then just convert it to a full color image and be able to store the color. We'll handle that internally for you.
Is there a list of which formats you support? So would it be really YCBCRA, would you support that, for example?
And the question is, do we support things like YCBCR?
YCCK.
There is support internally for that, but it's basically, I don't think we use it for JPEGs. I think we use it more for MPEG. But there's nothing to stop us architecturally from supporting that. So what you're asking is more, what do we do right now, which could change as the needs are expressed. We could, more optimally support those formats, but this API does not expose whether we're doing that. And if we ever found it necessary to support YCBCR internally for performance or quality or whatever, and people were reading and writing those kinds of images a lot, we could add that to the list of supported formats. But you will always be able to get an ARGB version of a pixel because the APIs provide that. It might require conversion, but that way you don't have to worry about what we're doing internally. But for those people who want to worry about it, that's all work and APIs that are TBD. And I think we're on the last couple of minutes. If any last question, otherwise we can just break for discussion and let you get to the next talks. Okay, thank you.